temperature. And all that heat, where it is going, there was a study by Levitas in 2012, which said that almost 90% of the excess heat because of the greenhouse gases are absorbed by the oceans. And if you don't have the ocean, what we have now, then the temperature will be already higher by 36 degrees centigrade. So if you are expecting like 37 degrees centigrade now in Indonesia, so add 36 degrees centigrade to that. So it will be completely inhabitable if the oceans are not absorbing the heat. We are lucky that oceans are absorbing the heat. And most of that absorption is happening in the upwelling zones. Because cold water is coming up, so it's absorbing the sun's excess radiation, the long wave excess radiation because of the greenhouse gases. And that's how we are maintaining the temperature what we are seeing now. The next question is whether the rise of temperature is uniform everywhere, or it is more in some places and less in some places. You can see that the trends are here from the Hartley Center SST. Higher temperature is in the mid-latitude northern hemisphere and mid-latitude southern hemisphere. And actually, instead of a warmer Eastern Pacific, you are expecting a cooler Eastern Pacific in this trend, 1980 to 2022 trend. But if you take a longer trend from 1958 to 2022, you can see like uniform rise of temperature in everywhere in the global ocean. And we know that the temperature is rising uniformly for past many thousands of years. And some of the regions were actually under the sea. Now they're exposed because we went through the little ice age when the sea level actually gone down. And now it is coming up again because of the global warming and rising of sea level. And many people attribute to that sea ice melting, but it's not necessarily that is the reason. It's because of heating, the water is expanding, and also the rainfall and river discharge also contributing to the higher sea level. And this is one of the studies which shows which are the regions which will be most affected by 2100. And you can see that most part of Asia will be mostly affected by the sea level rise, including Indonesia, especially Jakarta, which is the most populous city in the world now. And not only it is increasing the sea level, but also increasing the acidity, because oceans are also absorbing the carbon dioxide from the atmosphere, excess carbon dioxide from the atmosphere. And that is making the water more acidic. And the acidification, you can see the projected acidification, like most part of those ecosystems will be affected by the acidifications. And on top of that, we are also experiencing hypoxia, less oxygen in many upwelling zones. So combining sea level rise and then acidification and the hypoxia, many ecosystems will be actually affected by this global warming. Now, can we say that the models or what we are estimating at this moment, based on our assessment, can we say that the temperature rise will be 1.5 degrees centigrade, 2 degrees centigrade, 3 degrees centigrade, or 4 degrees centigrade? It depends on the sensitivity of the Earth. At this moment, we are not sure how sensitive is our system. So that's why we are kind of giving two estimates. If the Earth is low sensitive, the rise of the temperature because of the 2.5 watts per meter square rise due to the global warming will provide us like 0.5 to 0.7 degree centigrade temperature rise. But if the Earth is highly sensitive, then the temperature rise could be 3 degrees or 3.5 degrees higher than what we are experiencing now. So depending on how sensitive our Earth system, we can either get a very high temperature rise or moderate temperature rise. And that's because you can see from this example how the sensitivity is, Earth's sensitivity can affect that temperature rise. For example, you take the example which you can see on your right, this one. So more CO2, higher temperature, that will melt the ice, both sea ice and land ice. And if ice are melted, the albedo will be lower because it will become darker. So Earth will absorb more heat, and that's why the temperature will be higher. And that will provide a positive feedback. Higher temperature, even more snow melting, and more darker planet. That's why it will give us a positive feedback with a very high rise in temperature. But if you consider like the other scenarios, if higher temperature, we can have more evaporation. More evaporation will lead to more moisture in the atmosphere, so more clouds. And clouds can reflect back the sun's energy. That's why the temperature can cool down, and that will be a negative feedback. The other way, like water vapor also like greenhouse gases, it can absorb the long wave radiation. That's why the temperature might go higher. So we don't know which path the Earth will take. And depending on that scenario, we can expect a different rise in temperatures. There are also oceanic contribution to that uncertainties in the rise of temperature. Like we have these overturning circulations in all the basins, Atlantic Ocean, the Indian Ocean, the Pacific Ocean. And that overturning circulation can be shallow or deep. If it is shallow, then the mixed layer will become stable, and the temperature whichever is absorbed by the oceans will be only in the top 50 to 100 meters. That means warming will be stronger. But if the deep overturning is taking place, then the cold water can come up and can ventilate the heat we are absorbing at the surface, and that will lead to less sensitive Earth, which means the temperature rise will be moderate or normal. Now, is global warming the only factor that is causing the temperature rise? Actually, historically, if we see, the temperature has been higher, much higher. Temperature and carbon dioxide were much higher millions years ago. And that gradually shifted toward the comfortable temperature of 15 degrees centigrade, what we are seeing in the present, like 20,000 years to 30,000 years cycle. And we have different kind of natural processes that can contribute to global warming or cooling that are of the cycle of 1,000 years, 4,000 years, 40,000 years, and even shorter scales. Depending on different kind of processes, whether it is elliptical orbit or more circular orbit, we'll have one kind of natural climate change. And the tilt of the Earth, 23-degree half, is also not constant, it changes. So if it is lower or higher, depending on that, we'll get more heat or less heat, and that's why naturally, and that's why we can also have natural climate change. And the evolution of the society is somewhere or other dependent on that kind of natural processes. On top of that natural climate variations, climate change, we are also adding the anthropogenic gases, so that's adding complexity to the system. Now coming to the climate variations, we know that there are many modes of climate variations. One of the most dominant mode of climate variations is El Nino. When the Eastern Pacific gets warmer than normal, we call that as an El Nino. And that happens because of the upwelling is weaker. The system is such that the ocean and atmospheres are coupled, and if there is some change in that coupling system, then the El Nino happens. And if the coupling system is stronger, the La Nina happens. I'll come to that later. Now, why ENSO and IOD matter? Because primary modes of interannual climate variability in the Indo-Pacific, those are the two most dominant modes. And they have strong impacts on monsoon, Asian monsoon, Australian monsoon, Australasian monsoon, droughts, floods, marine heat waves. And the uncertainties in the drivers for regional climate projections are dependent on how many ENSOs or how many IODs we may expect in the future climate. And then not only that, these climate phenomena like Indian Ocean Dipole, the El Nino Modoki, they also modulate the extreme events. You can see in this diagram, there are floods, there are droughts, there are heat waves, and those are linked. I have not included in this forest fire can also be included. Those are directly or indirectly linked to those climate phenomena, El Nino. There are many years when you have El Nino, you have droughts. There are many years when you have La Nina, we have floods. And also positive IOD years, floods, negative IOD years, floods and droughts. And also, El Nino contribute to the global heat waves. So El Nino kind of brings out the heat from the oceans and releases to the atmosphere. So the heat waves are also related to the El Ninos. And the global temperature rise are also linked to the El Ninos. If you have more El Nino in the future climate, the temperature rise will be much higher than what we are experiencing now. But if instead we get La Ninas, then the temperature rise will be moderate. Although we are producing same greenhouse gas, the temperature rise will be moderate, depending on whether we are getting more La Ninas in the future or more El Ninos in the future. Now the process, as I said, it is the El Nino process is something like this. So we have Walker circulation, which is like this. So we have trade winds, which is blowing from east to west in the Pacific, and the winds converge near the Indonesian region, and then they rise. When they rise, the water vapor they are carrying will condense. Then we'll have the clouds and the rainfall there, and the rising air will eventually spread out as divergence, and then we'll go back to the Eastern Pacific to sink there and complete this circulation called the Walker circulations. So as long as we have the Walker circulation, that will drive the water from the American coast to the Indonesian coast. So that's why this side will be cooler, because water is driven away, subsurface water is coming up, so it's causing upwelling and cooling there. And since water is accumulating on the western side, the temperature, the mixed layer, the heat content of the upper layer will be much higher, the temperature of the surface will be higher, so warm temperature there. Warm temperature will cause convergence and the helping the cloud and helping the Walker circulation. So this Walker circulation and the temperature difference between east and west are coupled. As long as they are working together through a positive feedback, this system continues. However, if we have any disruption, like this one here, we have some kind of wind coming from the Indian Ocean, and that will cause convergence, and that convergence will move eastward and eventually will kill the upwelling in the eastern side. That's why we'll have warmer temperature on the eastern side, and the El Nino will start. There are different mechanisms. The mechanism I already told you is this one, and the Behera feedback mechanism, when the winds are blowing from east to west and causing the Walker circulation, rise in air on the Indonesian side, Walker circulation, and the positive feedback between the ocean and atmosphere. That is the normal state. If it is stronger, it's a La Nina state, because stronger wind means more upwelling, so more cooling, and temperature will be lower. If it is lower, somehow we weaken that Walker circulation or reverse it, then the eastern side will become warmer, because the water will be driven to the American coast away from the Indonesian coast. So Indonesian side will be cooler, the American side will be warmer, and that will lead to the El Nino state. So this kind of Behera hypothesis is explaining the three phases of ENSO phenomena: normal state, La Nina state, El Nino state. However, it is not good to explain why you have that transition. It explains the three phases, but it doesn't explain why you have that transition. And there are other theories which try to explain that. One of them is Wurke's warm water buildup in the West Pacific. So Wurke found that before an El Nino happens, the warm water volume builds up in the tropical Pacific. And when it reaches a critical volume, then it is released to the eastern Pacific, and that's why the El Nino happens. That's one of the hypotheses why El Nino happens abruptly, not regularly, like what Biafini's hypothesis says us. So it is abruptly because the warm waters are accumulating on the ocean side of the Pacific,